Hello viewers, in today's class we are going to discuss one important topic from differential equations, that is formation of differential equations, right? So in this lecture we'll see how we can form the differential equations for the given curves, right? So let us start. So let us first take this problem number 1, right? So here the algebraic equation of the curve is given as y square is equal to 4a x minus b, right? And we have to form the differential equation corresponding to this curve, right? So for forming the differential equation corresponding to this curve, what we do, we first count the number of arbitrary constants contained in this algebraic equation, right? So this is the important point while forming the differential equations, right? So we'll count the number of arbitrary constants contained in the algebraic equation, right? So here we have two constants, right? So a and b are the two arbitrary constants, right? So what we will do, once we have counted the number of arbitrary constants, we'll differentiate this differential equation to the number of times, that is the number of arbitrary constants, right? So here we have two arbitrary constants, so we'll differentiate this equation two times, right? Okay, so we can write this as equation number 1. So now let us differentiate both sides. So here the derivative of y square, and here we have dy dx of 4ax minus 4ab, right? So now we know that the derivative of y square is 2y dy over dx, right? Because first we'll differentiate y square with respect to y, we'll get to y, then by chain rule we have dy over dx. So here we have dy over dx, 2y dy over dx, and here 4ab is a constant. The derivative of constant is 0 and the derivative of x is 1. So here we have simply 4a times 1, that is 4. So now here we have y dy over dx, and we can cancel this 4 by this 2. So we have 4a over 2, that is 2a, right? So now we have y dy over dx is equal to 2a, right? So now still there is one arbitrary constant, right? That is a. So we'll differentiate again at both sides, right? So now we have d by dx of y dy over dx, and here we have d by dx of 2a, right? So now see, 2a being a constant, so the derivative should be equal to 0, right? And here we have y and dy over dx. So here we'll make use of the product rule. So first function, then derivative of second function, and then the second function, that is dy over dx, and the derivative of first function, right? So now we have y d2y over dx2, this is the second derivative, and here we have dy over dx whole square, right? So now we see that this equation is free from these two arbitrary constants, and this is the required differential equation corresponding to this algebraic equation, right? So what we have done, we are given an algebraic equation of a curve. We have counted the number of arbitrary constants. In this case this is 2, a and b. So we'll differentiate this equation two times, right? So we'll get the second derivative in this case, right? And we'll try to eliminate these arbitrary constants, and to get an equation which is free from these arbitrary constants, right? And from this equation we see that the order of this differential equation is 2, right? Because the highest order derivative occurring in this differential equation is 2, right? And the exponent of this highest order derivative is known as the degree of this equation, right? So the degree is 1 and the order is 2, right? And the order of the differential equation in this case is also equal to the number of arbitrary constants contained in the algebraic equation, right? So now let us consider this second problem. So here we have y is equal to a over x plus b, right? And here also we'll count the number of arbitrary constants, right? So here we have again two arbitrary constants, that is a and b, right? So we have to differentiate this differential equation at two times, right? And while differentiating this equation 1, we try to eliminate these arbitrary constants, right? So the final equation, which is the differential equation of this curve, should be free from these two arbitrary constants, right? So let us differentiate both sides. So here we have dy over dx. So a is constant, so we have derivative of 1 over x, and here the derivative of b is 0, right? So now we have dy over dx, and here the derivative of 1 over x can be written as x raised to minus 1. So this is minus 1, x minus 1 minus 1, that is minus x minus 2, that is minus 1 over x square, right? So the derivative of 1 over x with respect to x is minus 1 over x square. So this is minus a over x square, right? Now we have obtained this equation number 2, and this equation still contain an arbitrary constant, right? So what we will do, will again differentiate equation 2 both sides, right, with respect to x. So here we get d by dx of dy over dx, and here we have minus a and the derivative of 1 over x square, right? So this is the second derivative, and here we have minus a, and the derivative of 1 over x square is, that is 1 over x square is x raised to minus 2. So this is minus 2x minus 2 minus 1. So this is minus 2x minus 3. So this is minus 2 over x cube, right? So here we have minus 2 over x cube. This is 2a divided by x cube, right? So now we see that we have obtained d2y over dx2 is equal to 2a over x cube, right? So from this expression we can write it like this, 2 over x cube, and here we have a, right? And this a can be eliminated from equation number 2, right? Because from this equation 2 we can write a as taking x square to this side. So we have minus x square dy over dx, right? So our aim is to eliminate the arbitrary constants, right? So in the second derivative, the arbitrary constant it is still live, right? So we have to eliminate this a by using equation number 2, right? So now we can write the value of a. So here we have minus x square dy over dx, and here we have 2 over x cube, right? So now we can write d2y over dx2, and this x square and this power get cancelled. So we are left with minus 2 over x dy over dx. So taking this term to this side, we have d2y over dx2 plus 2 over x dy over dx is equal to 0, right? So this is the required differential equation corresponding to this curve, right? And again we see that here the order is the highest order occurring derivative, so the order is 2, and the degree of this differential equation is 1, right? Because the degree is the exponent of the highest order derivative occurring in a differential equation, right?